Cool. I'll draw a lot of graphs today since it's really easier to understand the linked list if you can see the graph. Let me start from here. I'll use my terminal for the whiteboard. Cool. Annotate, and I can draw. Okay, so let's assume we have the following data structure. We have a chain of boxes. Every box has two internal properties. One is value. That's an actual value of this node. We'll call this box as a node. So every single node has a value. It can be any type value you want. You will specify this whenever you allocate the linked list. We'll use integers because it's easier to show things with integers, but it doesn't really, it is not limited to integer. It can be string, it can be your class type, it can be character, whatever. So that's just a value that is stored inside this node. However, there is one more important property, which is a pointer to the next node. What do I mean by that? This chain, this data structure, is not structured in a way as, let's say, array structure. It doesn't have any index. The only thing it has, every node has a pointer to the next one. So by iterating one by one, you can reach any node you want, but you cannot jump over nodes, right? If you want to reach third node, you can only start from the first one, then move to the second one, and then move to the third one. And that's a feature, not a bug. So second node has exactly the same thing. It has some value, let's say integer value, and it has a pointer to the next one. The third one has as well value and the pointer to the next one. And the last one will be null. That's how we can know that it ends. Moreover, there is some terminology I would like to provide here. The very first node is called head. This is a head of your list. Let's say that's our head. And again, those nodes are not structured in your memory in terms, we don't know how they are stored. We just know that we have a pointer on the first one, and then the first one points to the second one, and the second one points to a third one, and so on and so forth. But we have no idea where it is stored and how it's structured in the memory. We can just iterate by pointers. Sometimes the last one is called tail, and maybe we can even have the pointer, which is called tail. Some linked lists will allow you to do that. Tail. This is our tail. Moreover, this is called single pointer linked list because we have only single one pointer to the next one. Sometimes there is double pointer, which means there is a pointer to the next one, and there is one more pointer to the previous one. That's a double pointed linked list, but it's not very popular, and I've never heard somebody was asked about double pointer on the real interview, but everything can be. It is a more or less valid data structure, so If you have time, feel free to check it out on LeetCode and other resources. We will focus on single one because it's much more popular. Here's it. What else? What else can be mentioned here? So every node has a value. It can be any type, but all the nodes obviously have same value type, right? Then it has a pointer, and that's it. Any questions at this point? Before we move to an implementation, do you have any questions? What's going on here and how it is? What are the rules of linked list? No? Okay. Can there be several pointers? Yeah, I mentioned that there can be 2 pointers. There is an option with 1 pointer, you can see it on the screen, and there is one more option with 2 pointers, double pointed linked list. In that way, every node has a pointer to the next one and to the previous one. So every node has 2 pointers then. And I've never seen more than 2 pointers. It doesn't make any sense. It becomes a graph, not a linked list if there is more than 2. Great. I'll clear it out. I'm opening my IntelliJ IDEA. Here we are. Great. We went through binary search last time, so this time I'm creating a new Java class and I will name it linked list. So linked list. This will be our class that implements linked list data structure. Means it should have some sort of public API that allows us to do several things, such as add a new node, print the whole linked list, maybe add node at start, and some other stuff. Now, first of all, how to represent the node inside the program. To do that, we are going to create a separate class. The separate class will be list node. And the list node will have obviously the value. Let's say it is integer, doesn't really matter. We can actually use class inside class. That's just a like small class that will be used in the implementation, so we can do that. List node that has a value, first of all, then it has the pointer to the next node. What is the data type of that pointer? How to represent the pointer? Do you have any ideas? Please Slack if you do. Any ideas? So how to represent the pointer to the next node? By allocating this class, list node is one box that I draw, right? That's exactly one node that should have the value inside and the pointer to the next node. So how to represent this pointer to the next node? What will be the type of this pointer? Yes, exactly. Java implicitly uses pointers, so type is list node. Our next one will be a list node. So that's a recursive allocation of the next thing, right? So what is it? What is next? Next is the same class, list node, that has a new value and the new next, which is the list node that has a new value and new next, which is the list node, and so on and so forth, right? So basically your next is your next box, and the type of the box is list node. That's important. That's it for list node. The only thing I want to add here is to create the constructor. So I don't need, I just want to create a constructor that will take a value and say this value equals 1. Just a regular constructor that takes value and creates the list node. So as you can see, the only thing that it takes is value. So next is null by default. Good. What else? So that's all for the list node, for the small box. Now, how to define the whole linked list? We define the one tiny part of it, right? And now we somehow need to define the whole chain of those list nodes. How to do that? To do that, we are going to have multiple properties and multiple methods inside linked list. For example, I mentioned that one important part of linked list is head. Tail is totally optional. Some programs just do not use it at all. However, the head is important because you need to have the point of start, right? You have to see what's your first node that points to the next one. And that's exactly what head is doing for us. Now, let's start from printing the whole linked list. So the first method I want to implement is a void method that just prints linked list. And again, this is a part of the class linked list that has a property head. So we know where to start. The whole idea of linked list is to use recursion to iterate through the list. There is no way to iterate. I mean, it's not even recursion in terms of we use recursion less times. It just, you have to move through the pointers to check out every box. That's an idea. There is no index like in array, let's say, right? It's just a different data structure. So how to print it? We can say that let's copy the head. For example, we'll use TMP a lot here. So some temporary, let's create temporary node that is copy of head, just to, so we are going to move this pointer slowly to the next pointer. And always remember that you probably want to leave head where the head is. So I don't want to mess up the head, because head should point to exactly first list node. So I'll just create a copy to play around with the copy instead of head. Now, I mentioned that the whole linked list ends up with the now. That's how can we determine that list is ended. We will see the now as somebody's next pointer. So basically we can say while, and while the condition here will be, we are going to move slowly TMP to the next pointer, and at some point our TMP will be now. So the whole idea of the end condition here is I want to print out while TMP is not now. While TMP is not now means there are more nodes before end, so we can iterate through them. So while TMP is not now, we can print out the value, let's say, or it doesn't really matter, right? So we can print out the TMP value. And moreover, we can say, we can print out the arrow, so it will smoothly print out all the values separated by arrows. And after we printed the TMP value, we need to move the TMP to the next one. So how to do that? Basically, that's our node, that's our new node, that's our new node, that's our new node, and that's a now. Every box, as I mentioned, has a value inside and the pointer. So that's a head right here. And that's a head. How to move this pointer? So you can see here that we created a copy of head. So we basically created a TMP that points to the same first node as head, because right here we created list node, TMP equals to head. So our TMP shows here. We print out the value, and then I want to move this TMP to the next one. I can do that by saying TMP equals what? Do you have any ideas here? TMP shows to this node, and I would like TMP to show to the next one. So how to move this pointer from here to here? Exactly. So our TMP is what? Is the list node. So that's at this node. Means this TMP has two things inside. It has value and it has next. So if I say TMP equals TMP.next, means take TMP and assign it to whatever is TMP.next. And TMP.next is exactly what we are looking for. It's our next node. That is the whole trick. That's how we can iterate through the list. So TMP equals TMP dot next. Cool, that's it. So we can say just print an empty line, so we can see our chain separately. And that's basically it. Now Let's double check what's going on here. So let's try to create the unit test, linked list test, which is not that easy here. Basically, I will create manually, I will create the linked list. I'll link all the nodes manually, and then I'll just print it out and see if I printed correctly. The idea is simple. So I can say that a list node first print allow test. There will be no actually test, it just will print out the linked list. So list node first is, I just want, can I, there cannot, oh, class, nice. I'll just move the list node to a separate class so I can access it directly from everywhere else. Oh, it's private now, right? And I cannot have two public classes in one thing. Should be declared in file name list, of course. Okay, then let me just create a new Java class, list node. And I'll move the implementation of the list node itself to a separate class. Here it is. So I have separate class list node. I didn't change anything, so it has the value, an integer value, and the list node next, and the constructor to create the list node. Meanwhile, here I'll just use the head, and we created the print linked list, our first method implementation. Now, linked list here, we'll just create a first list node. New list node 3, something like that. Okay, so 1, then I'll create second, 2, then I'll create, let's say, third, fourth, and fifth. Third, fourth, and fifth. So for test, I'll just manually create those nodes for now, because we don't have any public API to add nodes. We will add it soon. And then I'll say that that first one, let me think. So a linked list will be a new linked list. And then I'll say that linked list.head equals, it should be public though. So linked list.head equals first, and then first.next. Everything should be public. Public. Actually, this one should not be public value. It can be internal. Cool. So first dot next equals second, and second dot next equals third, and third dot next equals fourth, and fourth dot next equals fifth. So that's just a manual way of creating linked list, right? Because right now we don't have any other way. And now I just want to say linked list dot print linked list and see what will be printed. Here it is. 1, 2, 3, 4, 5. Actually, let's print now in the end. So in the end, I'll print now. Cool. Let's run again. I'll see 1, 2, 3, 4, 5 now. Bingo. That's great. That's great. What if I will have an empty one? I can create an empty list just by deleting head equals first. So this linked list has no head, means it's empty. So I'll just say null instead. Perfect. It does work. Do you have any questions so far? Please provide plus in Slack if you're good and you understand what's going on. How can this be used for practical tasks? Good question. There is, let me think. So there is some need to have, okay, let's think it that way. That's just a data structure, right? So that's just a special data structure that allows to store things sequentially. I cannot think on any problem on top of my head that requires you to save data in that way, but I'm sure there can be some. I can try to prepare some for the next lesson. I'm sure there can be some problems that are easier to solve if you store them in this sequential way. For example, if you are not sure of the capacity of your data in advance, and you just need to store as it is in a runtime. So some new data comes to you, to your processing, and you have to store it. Then it's really hard to allocate the array from the scratch because you are not able to know, you don't know the capacity of that array. And maybe some linked list helps to solve this. Yeah, I'll try to think of some real practical example. So far, we are talking about algorithms, right? All those algorithms are implemented already by Java developers, by Swift developers, doesn't really matter, by some developers. We are here to know how to pass the interview. That's the main question. And the real interviewers ask, please implement the linked list. Okay. Let's move on. We know how to print things. The next step, the logical step, is to add a node. So let's create, that doesn't really work like that, like this. We should be able to add the node using the API of our linked list. And we will do that. So I'll add one more method, a new method, add node. Do we need to return anything? Probably not, right? That's just an addition. So we can use a void function. Add node, and let's think what is our argument. What is our argument here, guys? What is an input for add node? List node. That's true, but if our API means let's add our a new node to the end of our linked list. Do we really need to provide the whole list node to our structure? Probably not. We can just take an integer value and we will create the list node as a next step. And we'll create the list node as a next step. So what is our logic inside? We have two options here. The first thing is, what if our head is new, is now? This means basically that we don't have any nodes yet. So our node is the first one. Right? Temp next. Yes. So this really depends on do we use tail or no. If we want to use tail in our structure, this is even easier, because in that way we know exactly where our linked list ends, and that will save a time complexity for us, because we don't need to iterate through the whole linked list to get the last element. So let's use that. I'll say public list node tail now as well by default. So that's just a pointer to the last node in our linked list. It's not used in print, right? We don't really need it in print. However, in the add node, we will use it. So if the head equals to now, means there is no node yet. We have a 0 node list for now. Then we can create a new list node. Node equals new list node with value that is provided as an argument here. And basically our head, or let's use TMP, our same syntax is here. So our head is TMP. And our tail is TMP, because this is a first node, right? So head and tail are both TMP. We have just one node, head is this node, and tail is this node. And the whole list, linked list contains just one node. That's the first case, if that's a first node we add. However, there is another case, if there are some nodes there inside already. Means our node is not the first one. We just need to add it to the end. But we have a tail, right, that we can use. So basically, if that's not the first one, then we can say that tail.next equals a new list node. And our new list node is a new tail. So now the tail should be moved to the next one. Tail equals tail.next. Basically, let's draw it out. That's a head, and that's a tail. That's a head and that's a tail. Whenever we say that we are going to add a new list node to the end, we say that tail.next, which is this guy, is not now anymore. It's just a new list node, not a now, with value. that is provided here. And now the tail should point to this guy instead of this. And we know already how to do that. Tail equals tail.next, because tail.next, this guy is tail, this is next. So tail.next is a new node we just added. So everything is logical here, but I know for those folks that see it for the first time, it can be mind-blowing, to be honest. But you should play around with this by your hands to feel it. Let's test it out. So now it should be much easier because we can just create the linked list. By the way, do we need to create the constructor? No, probably not. Okay, so we can say that the linked list is a new linked list, and we are going to test what? Add node test. And we are going to say that linked list dot add node with 1, then 2, 3, 4, 5. Much better now. So API, public API of our linked list makes our life so much easier, right? We don't need to do this mess anymore. We can just add new and new nodes, and basically it will automatically understand if there is no node yet, it will create the first one and point the head to it. If there are some nodes already, it will just add those nodes in the end to the end. Great. What else? Let's just print things now. So that's not a real unit test, but that's okay for now. By this day, we definitely know how to write unit tests. We wrote, I don't know, dozens of them already, so we can play around with this. 1, 2, 3, 4, 5 now. Perfect. Works. Let's create one more method. Our new method will be add. By the way, let's talk about the complexity. We totally forgot about complexity. What is the complexity of printing linked list? What is the complexity of this algorithm? How do you think? How many operations do we do? Yes, it's just a linear because we will go through exactly n times where n is the number of nodes. So big O of n. And what is the complexity of adding the node right now? Yes, it's a constant. We don't spend any time here. We just immediately adding the node here and immediately adding the node here. So it's a constant. Great. So let's do one more. Let's try to do add, let's see, add node at start. So add node at start. Same thing, we're providing this value, and I want to create the new node in the front. So my new head should be this node. My new head should be this node. Same idea. We have two options here. If head equals to null, means there are no nodes yet. And if head does not equal to null, means there are many nodes already, and we just need to move them to the from somehow and insert one more in the beginning. So if the head is null, then we just create this node with value, obviously, right? So this value that we provided. And now I can say that, let's just use everywhere TMP because we use TMP here and everywhere. So our TMP node means, actually, whenever head is null, everything is super simple because there are no more nodes. This is just an only node we have in list. Means both head equals TMP and tail equals TMP. Straightforward because there is nothing else you can point them to. And if there are some nodes already, then it's a bit more interesting. We can create the TMP node as well for value. And now we should somehow, let's think. You have this that points to this, that points to this, that points to now. This is tail, and this is head. And I would like to insert a new node here. So I create this node, TMP, how to change this node to my whole list. So what should I do to do this pointer to here? Give me some ideas. What can we use? So tmp.next means this pointer equals to head. So that's correct. We'll bind this tmp.next to the head, and then head should be moved to tmp. Exactly. Those two actions should be done, and there is no more this pointer. This is our new head, and that's our chain. Perfect. So what should we do here? We should say that tmp.next equals our previous head, and our new head is our tmp. Great. Let's test it out. What is the time, by the way? Exactly. Everything is constant. That's a huge pros, right? Everything is super fast in this data structure so far. So basically we can say that let's add 2, 3, 4, 5. And then I want to say add node at start with 1. So I just started from 2, 3, 4, 5. And then, sorry. 2, 3, 4, 5, and then I insert add node at start with 1. I should see my command 1, 2, 3, 4, 5 again. Add node at start. Great. Looks like it does work. Now, this is, by the way, this is extremely popular topic. There are dozens of different problems related to linked list on the LeetCode. So today we're covering basics, and next time we'll go through some interesting problems with LinkedIn, what we call medium one. The only thing we can add to the linked list today is we can implement remove node. So let's implement the void function that removes node and there are many different nodes we can delete from the linked list, right? So it depends on the problem itself, but usually we can say that there will be an argument, delete node, and there will be an argument which is list node. So I can specify that there is some special node I would like to delete from my chain. And I need to implement how I can do that. So obviously, this is a little bit more complicated problem than we've seen here. First of all, we have no idea where this node is located. And secondly, it's really non-trivial how to delete it because it's inside the chain. So we should repoint everything inside. We should repoint everything inside. So the idea is we have a linked list. And we are given with some arbitrary node inside. We are given with some arbitrary node inside. The question is how to remove this particular node so the other parts can be repointed to each other. So I would like to give you a couple of minutes so you can think about it. Obviously, the one way is to iterate through every single node from head, but actually no, it will not help anyway. So the solution here is pretty much elegant. Do you have any ideas? We're dealing with this node, and somehow we need to eliminate it. But the problem is we have no idea who does point to this node from the outside. So it's really non-trivial. So let me help you. The answer is we cannot control this pointer because we don't have this element. We just have this node, and we have a next. So we can control everything that starts from here. What if I will take this value and move this value to here, and then I will just remove this pointer and skip the next node. So technically, I will not remove this node, but I will imitate this by copying the value from the next and skipping the next. So in the real life, I will remove the next node, not the same node. But by copying the value from here to myself, I will basically mimic the deletion of current node. So the solution is just take the value from the next one. So take the value from the next node and assign to myself, and then just skip the next one. Instead of removing myself, I'll just removing the next one by saying that my next one is my next dot next one. With this line, I just skip next, right? Because whatever was next of the next is now my next. Basically, I just skip node next. That's it. It is really cute solution. Let's try to test it out. To do that, I'll probably use the same first setup we created here. So I can have the real nodes and I can remove some. So let's say I can delete node test. So I create this first, second, third, fourth, fifth, blah, blah, blah. And then I can say linked list, delete node, and I can say fourth, for example. So I should see 1, 2, 3, 5 now. 1, 2, 3, 5 now. The fourth one is removed. Do you also need to delete that next node to free up memory? That's a great question. I would say no in Java. That's a great question. I think Java will correct this automatically, no? Java is not my primary language, so I need to double check with that. But I think Java garbage collector will automatically deallocate it once nobody will point to this node. So it will just free it up automatically. What if we need to remove the tail? Good question, very good question. So let's assume I will try to remove the tail. Instead of delete node fourth, I would delete the fifth, which is tail, right? In that way, delete tail node test. Let's test it out. Great unit test, perfect. And test failed. Good point, really good point. So what can we do in that case? If we are given with the tail, we can just say that this node is now. Actually, this problem is from lead code. So let me show you the question. The problem statement on the lead code says, write a function to delete a node except the tail. Very good case, right? Thank you for your question. This doesn't really work if you are interested in deleting tail, because you have no pointer from the previous node and you are not able to remove the tail with that. So it works for every node except the tail, and the problem statement implicitly says about that. Sorry guys, I didn't tell you. We can try to submit our solution though. So let's open our implementation, delete node. Very concise, right? And I'll just submit to my lead code. Run code. And submit. As you can see, last time I submitted was 2 years ago. Accepted. Cool. And runtime is 0 milliseconds, faster than 100% of Java 9 submissions to delete node in linked list. That's a great result. I don't really think there is any other solution here, but anyway. Great. So that's it for our basic implementation. Please note we do not have a class next Sunday since 4th of July.